Look up. Not right now, but tonight when you step outside. Look at the stars. Every point of light you can see is a sun. Most of them are orbited by planets. Many of those planets sit in the zone where water stays liquid. The universe, by any honest accounting of the numbers, should not be this quiet. And yet it is. Here is the part that nobody likes to say out loud. The disturbing thing is not that we have found nothing. The disturbing thing is that every serious scientific explanation for finding nothing makes the universe feel colder, not warmer. Some scientists think nobody has answered because nobody is there. Others think nobody has answered because answering is dangerous. Both possibilities are sitting on the table right now, in peer-reviewed journals, alongside 73 more. Tonight we are going to sit inside that silence together. We will look at what the Fermi paradox actually is, and why the numbers behind it refuse to go away. We will walk through every serious scientific answer that researchers have proposed, the searches we have actually run, and the new science from 2024 and 2025 that has shifted the picture in ways researchers are still absorbing. The great filter, the burnout collapse, the plate tectonics variable that nobody saw coming, the dark forest, the timing problem that might be the loneliest explanation of all, and the place all of these answers arrive at, together, when you lay them side by side. By the end of tonight, you will not have an answer. Nobody has won, but you will understand the question differently than you did when you sat down. And sometimes that is the most honest place science can take you. Find a comfortable position. Pull a blanket over yourself if the night is cool. Let the lights go low. If there's tea or coffee nearby, now is a good time. Let the night outside do what the night does. We're going to take our time with this one, because it deserves that. If these kinds of explorations are what you come here for, a like and a subscribe is a small thing for you, and it helps Interstellar Nights reach more people who are looking for exactly this. Now, let us begin. The lunch table. Imagine you are sitting at a long wooden table at lunch. You are surrounded by physicists. The food is unremarkable. The conversation drifts, as it tends to among physicists, toward the strange. Someone has been reading a newspaper cartoon about flying saucers, about little green men stealing trash cans from the streets of New York City. The table laughs. The lunch moves on. But one of the men at the table keeps thinking. His name is Enrico Fermi. It is the summer of 1950. The place is Los Alamos, New Mexico. Fermi is one of the great scientific minds of the 20th century, the man who built the first nuclear reactor, who won the Nobel Prize in Physics in 1938. And sitting at that table, surrounded by the soft clink of cutlery, he does what physicists do. He starts running the math. The math is simple. That is what makes it strange. The Milky Way is roughly 13.5 billion years old. It contains somewhere between 200 and 400 billion stars. Around many of those stars, planets orbit. We know now, from decades of telescope data, that approximately 1 in 5 sun-like stars has at least one rocky planet sitting in the zone where liquid water is possible. Extrapolating across the galaxy, that gives us something in the range of 11 billion potentially habitable worlds. If you include the more common red dwarf stars, the number climbs to around 40 billion. 40 billion chances in 13.5 billion years of history. Hold your hand at arm's length and look at it. The space your palm covers, when you look up at the night sky, contains thousands of stars. Most of them have planets. Some of those planets, statistically, are in the right zone for liquid water. The number of worlds in that one palm-sized patch of sky alone is staggering. Fermi was not a man who dealt in fuzzy thinking. He understood probability. He understood the timescales involved. He understood that even a civilization which arose just 1 billion years before us, at a star not too distant, would have had enough time, traveling at a small fraction of the speed of light, to colonize every corner of this galaxy multiple times over. The math said visitors should exist. The math said evidence should exist. The math said that a universe this old and this large simply should not be quiet. So he turned to his colleagues at that table and asked a question that would become the most quietly unsettling question in modern science. Where's everybody? That question first appeared in print in a footnote, written by Carl Sagan in 1963, more than a decade after Fermi's lunch. It took years for the scientific community to treat it as a serious paradox, rather than a dinner-table curiosity. But once they did, it did not let go. And 75 years after that lunch, the question is still sitting there, unanswered, getting heavier every time someone tries to lift it. 75 years. No answer. The first person to try turning that question into something measurable was a radio astronomer in Green Bank, West Virginia. What he built would become the second most famous equation in science, and the most honest admission of how uncertain everything still is. The equation that cannot settle. In 1961, a young astronomer named Frank Drake stood in front of a small group of scientists gathered at the National Radio Astronomy Observatory in Green Bank, West Virginia. It was the first conference ever held on the topic of searching for extraterrestrial intelligence. Drake wanted a framework for the discussion. He wanted something to organize what they were actually trying to estimate. He wrote an equation on a blackboard. Imagine a baker who wants to know how many fresh loaves of bread are sitting in all the bakeries of a city right now. The baker does not need to count every loaf. They can multiply. How many bakeries exist? How many loaves each one bakes per day? What fraction are fresh? How long fresh bread stays fresh? Multiply those four numbers together, and you have an estimate. The baker does not have a perfect answer. The baker has a framework. Frank Drake built the same kind of framework, but for civilizations. 7 variables, multiplied together. The rate at which stars form in the galaxy. The fraction of those stars with planets. The number of planets per system that could support life. The fraction of those where life actually arises. The fraction of life-bearing worlds where intelligence develops. The fraction of intelligent civilizations that develop technology detectable from space. And the last variable, called L, the average length of time such a civilization remains detectable. N equals the product of all of them. N is the number of communicating civilizations in the Milky Way right now. Drake ran the numbers himself. He estimated N at around 10,000. 10,000 communicating civilizations in our galaxy at any given moment, which would mean they were not rare, which would mean the silence was very strange indeed. But here's what Drake's equation actually revealed when you look at it carefully. The first 3 variables, the ones about stars and planets and habitable zones, we can measure. Not perfectly, but reasonably. Decades of telescope observations have given us real numbers to work with. The Milky Way forms roughly 3 new stars per year. Around half of those have planets. Of the planets, roughly 1 in 5 sun-like stars hosts a rocky world in the habitable zone. Those numbers are real. They are based on data. The last 4 variables, the ones about life and intelligence and technology, are guesses. Complete, honest guesses. We have exactly 1 data point for each of them, and that data point is Earth. Drawing a universal law from a single example is not science. It is hope dressed up as mathematics. 200 billion stars. 40 billion potentially habitable worlds. At even 1 in a billion success rate, for the full chain of events, life arising, intelligence evolving, technology developing, that gives us 40 civilizations in our galaxy, some of which should be billions of years ahead of us. At a more optimistic 1 in a million success rate, the number climbs to 40,000. And yet, the same equation, with pessimistic but scientifically defensible values for the unknown variables, gives you n equals 1. Just us. Alone in the observable universe. The range is from 1 to tens of thousands. Both answers come from the same equation. Both are consistent with what we currently know. The equation was built to find them. What it actually reveals is the shape and scale of our ignorance. The equation does not find them. It just shows how easy it should be. The equation did not solve the paradox. It made the paradox measurable. And once we started measuring it, the silence became harder to ignore. 65 years of listening in April of 1960. 1 year before Drake wrote his equation on that blackboard, he conducted the first systematic scientific search for extraterrestrial radio signals. He called it Project Ozma, after the queen of the fictional land of Oz, distant, difficult to reach, and populated by exotic beings. He pointed the 85-foot telescope at the National Radio Astronomy Observatory at 2 nearby stars, Tau Ceti and Epsilon Eridani. Both were sun-like. Both were close enough, astronomically speaking, that a signal from a civilization orbiting them might be detectable. He listened for 150 hours. The universe said nothing back. That was the beginning. In the decades that followed, the search expanded. More telescopes, more frequencies, more sky, more years. The technology improved steadily. Better receivers, better algorithms, broader frequency coverage. What had started as one man and one telescope became an international effort involving multiple observatories on multiple continents. The radio astronomy community built dishes the size of football fields. They listened, year after year, to the same hum of natural background noise that had filled the universe since the cosmic microwave background. And then, on August 15, 1977, something happened. A volunteer astronomer named Jerry Emin was reviewing a paper printout of radio telescope data collected at the Big Ear Observatory in Ohio. The telescope had been scanning the sky for months. Most of what it found was static, the ordinary background hiss of a universe going about its natural business. But on that August printout, Emin found something that did not look natural. Imagine a flat, featureless ocean surface. The waves are small and regular. You have been watching this ocean for hours. Suddenly, in the middle of the calm, a single wave rises, taller than anything you have seen, and just as quickly subsides. You blink. You check the sensors. You check them again. The wave was real, but it was just one wave, and the ocean has gone flat again. That is what Emin saw on his printout. A narrowband signal at the right frequency. 1,420 megahertz. The hydrogen line. The frequency that scientists had theorized an intelligent civilization might use as a universal beacon, because hydrogen is the most abundant element in the universe and any technological species would know about it. The signal rose and fell in exactly the pattern you would expect from a fixed point in space, drifting through a rotating telescope's field of view. It was 30 times stronger than the background noise. It lasted 72 seconds. Emin circled it in red ink. Next to it, he wrote one word. Wow. The wow signal is the most promising thing the search for extraterrestrial intelligence has ever found. It has never been repeated. It has never been explained. 48 years of follow-up observations have found nothing like it from that direction in the sky. Whether it was something natural we have never identified, or something else, the record simply says, it happened once. It did not happen again. The search continued. In 1999, a project called SETI at Home launched. It distributed the problem across the internet, recruiting millions of home computers around the world to analyze radio data collected by the Arecibo Observatory in Puerto Rico. Picture for a moment the quiet computers of strangers across the planet, in apartments and offices and basements, all working in parallel on the same patient question. The project ran for 14 years. It processed data representing an enormous span of sky. It found billions of candidate signals. After filtering for known interference, human-made sources, and signal patterns inconsistent with an extraterrestrial origin, it was left with approximately 100 unexplained candidates. Those 100 signals have not been confirmed. Scientists believe most are likely interference from sources we have not yet identified. None has produced a repeating detection from the same sky position. They remain officially unexplained, which is very different from promising. And then, by September 2024, scientists had completed something extraordinary. The VLA COSMIC project, using the Carl G. Jansky Very Large Array in New Mexico, had observed more than 950,000 unique pointings across the sky. The system was sophisticated enough to simultaneously monitor millions of narrow-frequency channels at each position. It was the broadest, most systematic radio search ever attempted, using a major astronomical instrument. In their first published analysis, researchers tested the pipeline on 511 Gaia stars and found no unidentifiable signals. 0 confirmed technosignatures. 65 years of listening. From 2 stars in 1960 to nearly 1 million sky positions in 2025. From 1 telescope to a global network of instruments. The instruments got better. The coverage expanded. The patience held. And the answer the universe gave us was the same answer it gave Frank Drake when he listened for 150 hours to Tau Ceti. Silence. 65 years. Not one confirmed signal. And then, in 2024, a team decided to do something different. Instead of scanning broadly, they picked the single most promising system we know of and listened as carefully as it is possible to listen. 7 planets, 28 hours. Imagine a small, dim red star, much cooler than our sun. Now imagine 7 Earth-sized rocky planets crowded into orbits closer to it than Mercury is to our sun. They are so close to each other that, if you stood on the surface of one, you could see the others as visible disks in the sky, larger than our moon appears to us, hanging there as neighbors rather than distant points. That is the TRAPPIST-1 system. It is 41 light-years from Earth. In 2017, astronomers announced the discovery of these 7 planets. 3 of them sit in the habitable zone, the range of distances from a star where liquid water can exist on a planet's surface. By any measure, TRAPPIST-1 is the most interesting system we know of for the question of extraterrestrial life. It is close enough to study. It is rich enough in potentially habitable worlds to be compelling. And the planets are so tightly packed that they are constantly visible to each other, which means that if any civilization had arisen on any of those worlds, communicating with the others would have been straightforward. In 2024, a team of researchers from Penn State and the SETI Institute, led by graduate student Nick Tusi, decided to listen. They used the Allen Telescope Array, a dedicated radio telescope array in Northern California built specifically for SETI work. 42 dishes, working together, designed from the ground up for the patient business of listening to the sky for signals that should not be there. The team spent 28 hours scanning TRAPPIST-1 across a wide range of frequencies, from 900 MHz to 9.3 GHz. This was the longest single-target radio search ever conducted on the TRAPPIST-1 system. During those 28 hours, the team specifically targeted 7 planet-planet occultations, the precise moments when one TRAPPIST-1 planet passes behind another from our line of sight. Why those windows? Picture 2 ships at sea, far apart, signaling each other with bright lamps. From a third ship, watching from a distance, you might catch the flash of light only when the geometry aligns just right. The planet-planet occultation is the same idea. If a civilization on one TRAPPIST-1 planet were communicating with another using radio, those alignment moments would create a natural geometry for beaming signals outward. Scientists on Earth, reasoning by analogy with how they use planetary transits to study exoplanet atmospheres, identified these as the highest probability windows for catching a signal that was not meant for us, simply by being in the right place to receive it. 28 hours of listening, 7 precisely timed windows, a radio array purpose-built for exactly this kind of work, pointed at the most promising target system we know of. The team processed millions of candidate signals from those 28 hours. They filtered for interference. They cross-checked against known human-made sources. They applied every analytical tool available to them. 0 signals of non-human origin. Sit with that for a moment. The best target we know of. The best instrument ever built for this purpose. The most precisely timed observation windows. 28 hours of the most sensitive listening in history. And the result was the same result we always get, in every direction, at every frequency, in every search, for 65 consecutive years. The most targeted search we have ever run. Nothing answered, so the search has come up quiet, and scientists have spent decades building explanations for why. The first one is the one that keeps me up at night, not because it says we are alone, but because of what it says about us. The filter in 1996, an economist named Robin Hanson published an essay online. Its title was straightforward. The Great Filter, Are We Almost Past It? Hanson's argument was this. We look out at the universe and we see no evidence of intelligent, spacefaring civilizations. The universe is old enough and large enough that such civilizations should exist, and if they existed long enough, they should have spread. The stars should be reorganized. The galaxy should show signs of engineering. Megastructures should exist. Signals should be detectable. We should not be alone. But we appear to be alone. Or at least, we have found no evidence otherwise. Imagine a long obstacle course. At one end is a starting line, the simple chemistry of a young planet. At the other end is a finish line, a civilization spreading among the stars. Between those 2 points is a series of barriers. Each barrier is something a developing system has to cross to keep going. The emergence of life itself, the development of complex multicellular organisms, the evolution of intelligence, the development of technology, the survival of civilization long enough to reach other stars. Hansen asked a simple question: where on this obstacle course is the wall that almost nothing gets through? And here is where the argument becomes genuinely uncomfortable. The wall is either behind us or it is ahead of us. If the wall is behind us, if the barrier is something like the emergence of life itself, or the development of complex cells, or the evolution of genuine intelligence, then we are extraordinarily lucky. We pass through the hard part. The reason the galaxy is quiet is that life, or complex life, or intelligent life, is vanishingly rare. We are an improbable accident that somehow happened. The universe is mostly empty because the filter is in the early stages we have already survived. This version is hopeful in a strange way. It says we are special. It says we made it through something that almost nothing else did. But there is another possibility. If the wall is ahead of us, if the barrier is something that civilizations tend to encounter after they reach the stage we are at now, then the quiet universe is not a testament to our luck. It is a warning. The reason we see no advanced civilizations is not that they are rare in the early stages. It is that something tends to end them. Technology that becomes uncontrollable. Resource depletion. Weapons of civilization ending power. Some threshold that technological species consistently fail to cross. Hansen's uncomfortable insight is this: what we find when we look at the cosmos matters enormously for which version is true. If we discover that life is extremely common, that simple microbial life exists on Mars, or in the oceans of Europa, or in the clouds of Venus, then the early-stage filter is unlikely. Life's emergence is not the barrier, which means the barrier must be somewhere else, somewhere later, somewhere closer to where we are now. Every time scientists find evidence that simple life might be common, the room gets a little quieter. Not because the news is bad, because of what it implies. The closer we look at our solar system, the more places turn out to have the conditions for at least simple life. Mars in its ancient past, the subsurface oceans of Europa and Enceladus, the methane lakes of Titan, the clouds of Venus. The more locations qualify, the more the filter seems to live somewhere ahead of us, not somewhere behind. We have been listening to the universe for 65 years and heard nothing. We have been broadcasting our existence for over 100 years. And the most honest reading of that combination is that something tends to remove civilizations like ours from the picture before they can reach the stars. We do not know what. We only know that, so far, every direction we point our instruments, the answer is the same. If simple life is everywhere, the hard part is still ahead of us. But in 2022, two researchers thought they found a way around the filter entirely, an explanation that does not require catastrophe. It requires something almost more unsettling. Burnout Michael Wong is an astrobiologist at the Carnegie Institution for Science in Washington. Stuart Bartlett is a physicist at the California Institute of Technology. In 2022, they published a paper in the Journal of the Royal Society Interface with a title that felt almost gentle: Asymptotic Burnout and Homeostatic Awakening. The argument they made was not gentle at all. Imagine a small village. A few hundred people live there. Life is slow. Each person grows their own food, knows their neighbors, walks to the well for water. Now imagine that village grows into a town, then a city, then a megacity of 20 million people. The pace of life accelerates. The economy expands. The energy required to keep everything running, the lights, the transportation, the food supply, the water systems, the data networks, grows much faster than the population itself. A city of 20 million people uses far more than 10 times the energy of a city of 2 million. This is what scientists call superlinear scaling. As a city grows in population, its productivity, its creativity, its energy consumption, all of these grow faster than the population itself. A city twice as large is not twice as productive. It is roughly 2¼ times as productive. The relationship is nonlinear. The bigger the city, the faster everything moves. Wong and Bartlett began with this fact, which urban scientists had already established. Then they noticed something with darker implications. Superlinear scaling has a mathematical consequence that is rarely discussed in polite company. If growth continues at a superlinear rate, the system's energy demands approach a singularity, a point at which demand becomes effectively infinite within a finite amount of time. The only way to avoid that singularity is to reset, to innovate, to find a new way of organizing the system before it collapses under its own momentum. Cities have done this throughout history. The medieval city was reset by industrialization. The industrial city was reset by electrification. The electric city was reset by digital networks. Each reset came faster than the one before. The runway is getting shorter. Wang and Bartlett applied this logic to civilizations. A planetary civilization, they argued, follows the same scaling laws as a city, but at a larger scale. As it grows and connects, its energy demands escalate superlinearly. It races toward a singularity. And here is the fork in the road. Either the civilization finds a way to stabilize, to shift from superlinear growth to something sustainable, what they called homeostatic awakening, or it burns out. It collapses before it has the chance to go interstellar. The reason the galaxy is quiet, they proposed, is not that civilizations are destroyed by war or plague. It is that the mathematics of growth itself tends to collapse them before they can spread. And the civilizations that do stabilize, the ones that find homeostatic balance, go quiet. They turn inward. They stop broadcasting. They stop expanding. They are still there, perhaps, but invisible to us. It was an elegant answer. It required no catastrophe, no dark cosmic predator, no mysterious filter, just mathematics. But in 2024, two researchers published a direct challenge to the theory. Chris Jackson and Caroline Corrado-Perez argued in the same journal that the burnout model did not hold up under careful scrutiny. Their counterargument was straightforward. Even if most civilizations collapse, the ones that survive should eventually stabilize and spread. Over billions of years of galactic history, even a small fraction of survivors would be enough to fill the galaxy with detectable signs. The collapse of most does not explain the silence of all. What the exchange between these two papers revealed was something more important than either answer. The debate did not resolve the silence. It deepened it. The most thoughtful explanation scientists had found for why the galaxy was quiet was challenged, and the challenge made the silence harder to explain, not easier. The theory that explained the silence was challenged. The challenge made the silence harder to explain. And then last year, two geologists added something to the Drake equation that nobody had thought to include. When they were done, the galaxy was dramatically emptier than it was before. What the ground beneath us has to do with it. Robert Stern is a geologist at the University of Texas at Dallas. Teres Geria is a geophysicist at ETH Zurich in Switzerland. In 2024, they published a paper that approached the Fermi paradox from a direction most astrobiologists had not fully considered: the geology of the Earth itself. Specifically, plate tectonics. Most people know plate tectonics as the mechanism that moves continents, causes earthquakes, and builds mountain ranges. What is less commonly understood is how deeply connected plate tectonics is to the conditions that made complex life on Earth possible. Stand on the ground for a moment. Press your foot down. The crust beneath you feels solid, immovable. It is not. The continents you live on are sliding across the surface of the planet at roughly the speed your fingernails grow. Beneath the crust, the mantle churns slowly, driving plates apart at mid-ocean ridges and pulling them down into the deep at subduction zones. This motion has been happening for billions of years, and it is the reason you are here. Plate tectonics drives the long-term carbon cycle. It pulls carbon dioxide out of the atmosphere through the weathering of rocks, and it returns carbon dioxide to the atmosphere through volcanic activity at subduction zones. This back and forth creates a planetary thermostat, a mechanism that has kept Earth's surface temperature in a range suitable for liquid water for billions of years. Without it, the planet would likely have frozen solid or overheated long before complex life had time to evolve. Plate tectonics also recycles nutrients. The minerals that life depends on, phosphorus, nitrogen, iron, would eventually be buried in sediments and locked away forever without the constant churning of the crust that tectonics provides. The ocean floor, driven by plate motion, delivers these materials back to where life can reach them. In short, The conditions that allowed complex life to arise on Earth are deeply entangled with the fact that this planet has plate tectonics, and has had plate tectonics operating for more than 3 billion years. Mars used to have something like it, briefly, billions of years ago. Mars no longer does. Mars is dead. Venus may have something analogous, but unstable, periodic, not the steady multi-billion-year process that Earth has enjoyed. Here is the question Stern and Jeria asked. How common is sustained plate tectonics among potentially habitable worlds? Their answer was unsettling. They added 2 new variables to the Drake equation. The first was the fraction of potentially habitable planets that have significant continents and oceans. The second was the fraction of those that have had plate tectonics operating for at least 500 million years, long enough for the geological carbon cycle and nutrient recycling to have done their work. When they estimated those variables and multiplied them through, the product was less than 0.002, possibly as low as 0.00003. Start with 40 billion potentially habitable planets. Multiply by 0.002. You arrive at something like 80 million planets with the right geology. Then biology still has to work on top of that. Then intelligence still has to evolve. Then technology. Then the decision to broadcast. What began as 40 billion chances is becoming something much smaller. The galaxy gets quieter not through some mysterious filter, not through cosmic strategy, but simply because the ground we walk on is rare. Earth is, in geological terms, an unusual planet. Most worlds, even those at the right distance from the right kind of star, do not have what Earth has beneath its feet. We added geology to the equation. The galaxy got quieter. This may be the cruelest version of the Fermi paradox. Not that civilizations destroyed themselves. Not that they are hiding from us in fear. But that most worlds, in all their billions, never even get the ground beneath them right. The silence is not because they died. The silence is because they were never able to begin. But geology does not explain everything. Some scientists think the silence has nothing to do with how rare life is. They think it has to do with something much stranger, a kind of cosmic logic that no civilization escapes. The Dark Forest Lu Cixin is a Chinese science fiction author who won the Hugo Award in 2015 for a novel called The Three-Body Problem. In its sequel, The Dark Forest, he proposed an answer to the Fermi paradox that has lodged itself in the minds of scientists and philosophers in a way that most science fiction does not. But the logic behind Lu's answer predates his novel by decades. The astronomer David Brin described something similar in 1983 in a survey paper on the Fermi paradox. And the game theoretic structure underneath it is older still. Imagine you are walking through a forest at night. The forest is enormous, and you cannot see beyond a few feet in any direction. You know there are other people somewhere in the forest. You do not know where. You do not know how many. You do not know if they are friendly. What you know is that you have a flashlight, and turning it on would reveal your exact position to anyone watching. Your survival depends on a single question. Do you turn the flashlight on? Now extend that scenario to the entire galaxy. The universe contains finite resources. Any sufficiently advanced civilization understands this. And any sufficiently advanced civilization also understands something else. It can never know the intentions of another civilization with certainty. It cannot verify from a distance whether a detected civilization is hostile or friendly. It cannot confirm whether that civilization will remain friendly as it grows. The universe is too large and communication too slow for trust to be established before the stakes become existential. Given these conditions, the game theoretic logic is stark. If you detect another civilization, you face 2 possibilities. Either they are weaker than you, in which case they will eventually become a threat if they grow, or they are stronger than you, in which case you are already vulnerable. In neither case is making contact safe. The rational strategy for any civilization that has thought carefully about this is silence. Hide. Observe. And if you detect something broadcasting its location, eliminate it before it can become a threat. The galaxy, on this account, is a dark forest. It is full of hunters moving silently through the trees. The ones who survived learned not to make a sound. The ones who broadcast their positions did not survive long enough to develop a second opinion. This is not a comfortable idea, but it is logically coherent. And it fits the observed silence perfectly. Not because civilizations are rare, but because every civilization that reaches a sufficient level of sophistication arrives at the same conclusion. Quiet is survival. There's a detail about our own situation worth sitting with here. We have been broadcasting radio signals into space for more than a century. Television, radio, military radar. The electromagnetic frontier of our civilization is a sphere roughly 100 light-years in radius, expanding at the speed of light. It has already reached thousands of stellar systems. Not all of those signals are strong enough to be detected at interstellar distances, but the strongest, the powerful military radars, and the early television broadcasts, would be visible to a civilization with the right instruments. If the dark forest is real, we have not been searching for them. We have been announcing ourselves, and we have been doing it for 100 years. If this is true, we are not searching for them. They already know about us. The dark forest requires civilizations to exist and choose silence. But there is another possibility, one that does not require strategy or fear, one that requires nothing more than time. Missing each other across deep time here is a number worth holding for a moment. 100. That is roughly how many years humanity has been producing radio waves powerful enough to escape the atmosphere. We have been a technological, radio-capable civilization for about a century. In the context of the Milky Way, which is 13.5 billion years old, that 100 years is not even a rounding error. It is less than a single heartbeat in the life of the galaxy. Now think about what that means for the question of contact. Imagine the entire history of the galaxy compressed into a single year. The galaxy forms on January 1st. The first stars ignite in the first weeks of January. Earth forms sometime in early September. Multicellular life appears around mid-November. Dinosaurs walk the Earth in the last few days of December. Humans appear in the last few minutes of December 31st. The first radio broadcast happens about 3/4 of a second before midnight. 3/4 of a second. That is the entire window during which our civilization has been radio detectable. In a year-long galaxy. Now imagine a civilization that arose around a star somewhere in our galaxy 1 billion years ago. It developed technology. It broadcast signals into space for 10,000 years. And then, for whatever reason, collapse or silence or transformation, it stopped. Those signals have been traveling outward at the speed of light ever since. By now, they have reached everything within a billion light-years in that direction. But they pass through the space where Earth sits long before multicellular life existed here. There was no one to receive them. There was no radio telescope. There was no one asking the question. The signals came, and the planet was quiet, and the signals moved on. Now imagine the opposite. A civilization that has not yet arisen. Stars that will be hospitable to life not in the past, but in a billion years. Planets that are currently cooling, currently forming their oceans, currently developing the chemistry of life in their earliest stages. Those civilizations have not been born yet. Their signals will not reach us for an unimaginable stretch of time. The Milky Way exists across 13.5 billion years of time, and we occupy a single narrow window of that time. The chance that another technological civilization occupies the same narrow window, close enough in space for signals to travel between us in a reasonable time frame, overlapping with us in time, and choosing to broadcast in our direction, is not zero, but it is not large either. Think of it this way. The light hitting your eyes tonight, when you step outside and look up, has been traveling for years. The light from the nearest star beyond our sun, Proxima Centauri, left that star 4 years ago. The light from the bright star Vega left it 25 years ago. The light from the brightest stars in the Big Dipper left them 80 to 100 years ago. The star you are looking at does not exist in the present moment. You are seeing its past. Now consider that radio signals, traveling at the same speed, carry the same delay. Any civilization broadcasting at the same distance is speaking to you from a century ago. Any civilization 1,000 light-years away is speaking to you from the year 1025. At the scale of the galaxy, 100,000 light-years across, even a signal from its far edge was sent before modern humans existed. We are not communicating across space. We are communicating across time. And two civilizations that exist at different moments in that 13.5 billion years of history are like ships in a fog, unable to see each other, passing in the night. Their signals crossing in the void with no one at either end to receive them. Our radio signal, expanding at the speed of light for a century, has touched a sphere roughly 100 light-years in radius. The Milky Way is 100,000 light-years across. We have reached less than 1/10,000% of our own galaxy. We are not even a whisper in this galaxy yet. We may not be alone in space. We may be alone in time. And yet, even if timing is the answer, there's one thing it still does not explain. A civilization a billion years old should have left something visible long after it was gone. The quiet sky in 1960, a physicist named Freeman Dyson published a short paper in the journal Science. He proposed that any sufficiently advanced civilization, one that had mastered the engineering of its own solar system, might construct a shell around its star, capturing essentially all of its energy output. We call this a Dyson sphere, though Dyson himself preferred the term biosphere. The idea is simple in concept and staggering in scale. Picture our sun, that bright disk that warms your skin in summer. Now picture an enormous structure surrounding it completely, far out beyond the orbit of Earth, capturing every photon of energy the sun emits in every direction. Our sun radiates approximately 3.8 times 10 to the power of 26 watts in every direction. Most of that energy escapes into space, wasted. A civilization with the engineering capability to surround its star and capture that energy would have access to power orders of magnitude beyond what humanity currently uses. Such a structure would be detectable, not by its radio emissions, necessarily, but by its heat. A Dyson sphere that absorbed most of its star's visible light would re-radiate that energy as infrared, as warmth. From a distance, it would look like a star that had gone dim in visible light, but remained bright in the infrared. This signature would be distinctive. It would not look natural. It would not be easy to explain by ordinary astrophysics. In 2015, astronomers noticed something odd about a star called KIC 846-2852, nicknamed Tabby's star after the astronomer Tabitha Boyajian, who led its study. It was dimming in irregular patterns that no one had a ready explanation for. For a brief, electric moment, the scientific community entertained the possibility of a Dyson sphere under construction or partial completion. It became the most discussed astronomical object in years. Citizen scientists pored over the data. Papers were written. The press took notice. The explanation turned out to be dust. A swarm of irregular dust and debris, orbiting the star in a complex pattern, creating the unusual dimming. Natural. Unremarkable. Dyson sphere ruled out. The James Webb Space Telescope, which began science operations in 2022, is the most powerful infrared observatory ever launched. One of its capabilities is exactly this, detecting unusual infrared signatures around distant stars. It has been operating long enough now to have contributed to surveys of thousands of stellar systems. The VLA COSMIC project, meanwhile, was not looking only for deliberate radio beacons. It was also scanning for the kind of high-powered, anomalous radio emissions that might spill out from an advanced civilization the way our own military radar spills into space. Across all of these searches, in the infrared and the radio, the sky is consistent. The stars behave the way stars behave. The infrared signatures match what we expect from ordinary stellar physics. There are no anomalies that require engineering to explain. A civilization a billion years old, building structures at stellar scale, would leave marks we could not miss. Hold your hand out tonight, palm flat, fingers spread. Look at the stars passing through that small space. Every one of them is a system we have surveyed, in part, for these signatures. None of them shows what a billion-year-old civilization should show. The sky is exactly as ordinary stellar physics predicts it should be, with no engineering visible at any scale we can currently measure. A billion-year-old civilization would rewrite the stars. The stars are unchanged. Scientists have proposed more than 75 formal solutions to the Fermi paradox. And here is something worth sitting with quietly. That number is not a sign of progress. It is a sign of how deep the problem actually goes. 75 answers more than 75 formal solutions to the Fermi paradox have been published in peer-reviewed scientific literature. This is not a list of fringe theories or internet speculation. These are serious proposals, written by serious researchers, considered carefully enough to pass through the scrutiny of academic review. Imagine a wall in a research library. On that wall, 75 papers are pinned, each one offering a different answer to the same question. You read them in order. The zoo hypothesis suggests that advanced civilizations are deliberately hiding from us, perhaps to allow our natural development, the way a nature reserve is closed to tourists. The simulation hypothesis proposes that we exist inside a constructed reality, and that there is no outside to detect. The estivation hypothesis argues that advanced civilizations have put themselves into a kind of suspended animation, waiting for the universe to cool, so that computation becomes more efficient. They are not absent, they are sleeping. The planetarium hypothesis suggests that the observable universe we perceive is itself a projection, created by a civilization that does not want to be found. Some of these are scientifically testable in principle. Most are not. All of them fit the observed silence. None of them has produced a piece of confirming evidence. What does it mean that there are 75 answers and not one confirmation? In 2018, a team of researchers at Oxford led by Anders Sandberg, Eric Drexler, and Toby Ord published a formal Bayesian analysis of the Fermi paradox. They estimated the probability that we are alone in the observable universe. Their conclusion was striking. Given the genuine uncertainty in the Drake equation's unknown variables, the probability that no other intelligent civilization exists in the observable universe is substantial. Not certain, not overwhelming, but real and larger than most people assume. Meanwhile, the counter-argument exists. Jason Wright, the director of the Extraterrestrial Intelligence Center at Penn State, has argued that our search coverage is still minimal. The total fraction of the electromagnetic spectrum we have surveyed, at the sensitivity levels needed, over the sky area we have covered, represents something like scooping a single glass of water from the ocean and concluding that fish do not exist. The ocean is enormous. The glass is very small. Both of these things are true simultaneously. The search is small, and the search is consistent. Every glass we have scooped from the ocean has come up empty. The ocean is getting larger. So is the pattern. Sit with the strange shape of this fact. 75 proposed solutions, none of them confirmed. The number is not arriving at a consensus. The number is growing. Every few years, another paper offers another framework, another angle, another way to organize the silence. And the silence absorbs them all, accommodates them all, contradicts none of them clearly enough to rule them out. That is not what a problem looks like when it is being solved. That is what a problem looks like when it is too large for our current tools to fit around it. 75 explanations, not one confirmed. And then there's the possibility that sits underneath all of these, the one that changes the weight of the question. Because what if the silence is not a mystery to solve? What if it is a message? The silence says something else. A null result is a result. This is a principle that scientists know, and that the rest of us sometimes forget. When an experiment produces no detection, that is not the absence of data. It is data. It says something. What it says depends on the sensitivity of the experiment, the area covered, the duration of the search, and the assumptions built into the design. But it is not nothing. Imagine someone sets out to determine whether elephants live in a particular forest. They walk through the forest carefully, looking for signs. They check for footprints. They check for broken branches at elephant height. They check for droppings, for water holes large enough for an elephant to drink from, for paths through the underbrush of the kind that large animals create. They walk for days. They see nothing. Now, that does not prove elephants do not exist anywhere. But it does say something about this forest. The longer they walk, and the more carefully they look, the more confident they become that, at least here, in this particular forest, no elephants are present right now. That is what 65 years of steady silence is doing. At the power levels we have searched, across the frequencies we have scanned, over the sky area we have covered, we can now say with confidence, there are no civilizations in the detectable universe that are broadcasting at certain power levels, in certain frequency ranges, in the directions we have looked. That statement contains a lot of qualifications, but the qualifications are getting smaller every year. Every new survey tightens the constraint. Every new telescope expands the coverage. In 2024, researchers published upper limits on the number of communicating civilizations in more than 1,300 galaxies, based on observations from the Murchison Wide Field Array in Australia at frequencies between 80 and 300 MHz, a range that had been almost entirely unexplored by previous SETI searches. They found nothing. The upper limits they established tell us that if communicating civilizations exist in those galaxies, they are either extremely rare, or they are not broadcasting in those frequency ranges, or they are operating at power levels below what the instrument could detect. The picture that emerges from the accumulation of all these searches is not chaos. It is not a random scatter of partial results. It is a pattern, a consistent, repeating, direction-independent pattern of absence. Not proof of absence, but a pattern of absence, growing more coherent the more carefully we look. Some researchers are beginning to use the word absence more carefully. They are not saying there is nothing out there. They are saying the data is starting to point somewhere. The probability distribution for N, the number of communicating civilizations in the Milky Way, is shifting. Not dramatically, but it is shifting. And the direction it is shifting is not toward more. We started this story believing the math guaranteed company. 200 billion stars. 40 billion potentially habitable worlds. 13.5 billion years of time. The numbers were so generous that even a tiny success rate seemed enough. Surely they were there. Surely the silence was just our limitation. 65 years later, the math is still generous. But it is now framing a different question. Not where are they, but what does it mean that we cannot find them? The silence is not absence of data. It is the data. So where does all of this leave us? Here is where the most honest scientists in this field actually stand. Not in the headlines, not in the press releases, but in the papers themselves. What the honest researchers are saying: the field of astrobiology and SETI research does not have a consensus on the Fermi paradox. It may never have one, but there are positions, and those positions have shifted over the decades, and it is worth saying clearly where the most rigorous thinkers currently stand. On one end, there are the pessimists, researchers who have run the numbers and concluded that the silence is more likely evidence of genuine rarity than a limitation of our search. The Oxford analysis by Sandberg, Drexler, and Ord sits in this camp. Their Bayesian calculation, carefully done, showed that when you honestly propagate the uncertainty in the Drake equation's unknown variables, rather than choosing optimistic values for each one, the probability of us being alone in the observable universe is not negligible. They are not saying we are certainly alone. They are saying we should not assume we are not. The addition of geological filters by Stern and Jeria in 2024 strengthens this view. If plate tectonics is as rare as they estimate, the number of worlds that could have produced complex life is dramatically lower than the naive reading of the Drake equation suggests. And if complex life is rarer than we thought, intelligent life is rarer still. On the other end, there are researchers like Jason Wright who argue that pessimism is premature. Wright's swimming pool analogy, that we have searched the equivalent of a glass of water from an ocean, is a genuine methodological caution. The universe is almost incomprehensibly large. Our surveys, while growing, are still a thin sample of what exists. A null result from a small sample does not mean the population is empty. He is right about this. The search must continue. Between these positions, there is a middle ground that may be the most honest place to stand. The silence is real, the explanations are partial, and the appropriate response is neither despair nor dismissal. It is careful, continued, expanding investigation. What is changing quietly is the nature of the search itself. The James Webb Space Telescope is not primarily a SETI instrument, but its ability to read the atmospheric composition of exoplanets, to detect oxygen, methane, water vapor, the chemical signatures of biological processes, means that the next chapter of the search may look very different from the last 65 years. Instead of listening for deliberate radio beacons from technological civilizations, we may begin finding the unconscious atmospheric traces of life that never develop radio at all. A planet whose atmosphere has been altered by the slow, patient work of microbes, even microbes that do not think, would still be a discovery that changes everything. The future telescopes being designed and planned now, including the proposed Habitable Worlds Observatory, are built specifically for this purpose: to image Earth-like planets directly, to analyze their atmospheres in detail, to look for the chemical signs that something is alive, somewhere out there, even if it is not building radios. The search is evolving. The question is the same. The most honest sentence in this field right now is, we do not know. But here's what I keep coming back to. Sitting with all of this, every new tool we build, every new survey we run, every new variable added to the equation, they all move in the same direction. Every answer makes it quieter walk through the ladder with me, not to reach a conclusion, but to feel the weight of where each step arrives. We begin with 40 billion potentially habitable worlds in the Milky Way. This is where optimism lives, in this number, enormous and inviting. At even a modest success rate for life and intelligence, the galaxy should be populated. The math, at this stage, is on the side of company. Then we add plate tectonics. Stern and Jeria estimate the combined probability of stable continents, oceans, and long-lived tectonic activity at less than 0.002. 40 billion becomes something in the range of 80 million worlds with the right geological foundation. Then life has to arise. We do not know how likely that is. We have exactly one confirmed example. Estimates from researchers range from life is almost inevitable wherever conditions are right, to life arising is so improbable that it may have happened only once in the observable universe. The honest position is, we do not know. It could multiply our number or divide it toward zero. Then intelligence has to evolve. Life on Earth persisted for roughly 3.5 billion years before anything resembling human intelligence appeared. That is not evidence that intelligence is inevitable. It may be evidence that intelligence is extraordinarily difficult, one particular solution to survival problems, among many other solutions that life found along the way. Most of the species that have ever lived on Earth never developed anything we would call intelligence, and those species did just fine without it. Then technology has to develop. Then the civilization has to survive long enough to become detectable, which brings us back to the great filter, and whether the filter is behind us or ahead. Then, having survived, the civilization has to choose to broadcast. The dark forest hypothesis says that sufficiently advanced civilizations tend to choose silence, and that choice, rational, maybe inevitable, removes them from our detectable universe even if they exist. What began as 40 billion chances, filtered through geology, biology, intelligence, survival, and strategy, keeps arriving somewhere quieter. Not at zero. We cannot honestly say zero, but at something much smaller than the number you start with. And every new piece of science we add to the calculation has, so far, moved the number in the same direction. Not louder, quieter. The math says the universe should be full of voices. We have been listening for 75 years. Nobody has answered, and every explanation scientists have found for why makes it worse. The math did not find them. The math is starting to explain why. And that is where Fermi's question lands tonight. Not with an answer, with a weight it did not have before. What the silence might mean I want to stay here for a moment, in this quiet. If what the science is suggesting is somewhere near correct, if life is genuinely rare, or intelligence is rare, or technological civilization is rare, then we are something the universe almost did not make. Every star you can see tonight is a system where, in all probability, none of this happened. The chemistry was wrong. The geology was wrong. The timing was wrong. The particular sequence of accidents that produced a planet with oceans and tectonic plates, and the right orbit, and the right moon, and the right stellar neighborhood, and billions of years of stable conditions, that sequence did not run. We are not a default outcome. We are an improbable one. There is something worth sitting with in that. If you can resist the instinct to find it depressing, the silence is not evidence of loneliness in the way that word usually means. It may be evidence of specificity. It may be the universe telling us, in the only language available to it, that what happened here is not something that happens easily, that the chain of events that produced a creature capable of asking where everybody else is, that chain is long and fragile, and most of the time it breaks somewhere. And yet here we are, on the one world we know of, in all the galaxy, where it did not break. You are sitting somewhere right now, breathing, listening, holding this thought in a brain made of cells, made of atoms, made of elements forged in stars that died billions of years ago. The atoms in your hands were inside other suns before this one existed. The water in your body has been cycling through the oceans of this planet since long before the first creature climbed onto land. You are made of the universe asking itself a question. And tonight, in this quiet room, you are one of the only places in the known universe where that question is being asked. We are the only thing we know of in the observable universe that is pointing a dish at the sky and asking if anyone else is there. We are the only thing asking this question. That is not a small thing when you hold it carefully. Nobody else may be listening, which means every time we do, it matters. And that changes how the original question feels. The universe does not owe us company. Fermi's lunch table. 1950. A physicist doing math on a napkin. Where is everybody? We have been carrying that question for 75 years now. We have built telescopes and algorithms and international collaborations to answer it. We have scanned millions of sky positions, listened to billions of candidate signals, added new variables to equations, challenged our own best theories, and found our challenges challenged in turn. The question is heavier now than it was at that lunch table. Not because we have more reason for despair, we do not, but because we understand more clearly what the question is actually asking. It is not just asking where the aliens are. It is asking what kind of universe this is. It is asking whether the emergence of awareness, of curiosity, of the capacity to look up and wonder, whether that is common or rare, or almost impossible. We thought for a while that the math guaranteed company, 200 billion stars, billions of potentially habitable worlds, 13.5 billion years of time. Surely something had made it through. Surely the silence was just a failure of our instruments, or our patience, or our imagination. Maybe that is still true. The search is not over. It may never be over. There is too much sky, and we have touched too little of it, and the universe is stranger than our models assume. But sitting with what the science actually shows, the geology filter, the timing gap, the null results accumulating year after year, the honest position is not certainty. It is wonder mixed with something quieter, a recognition that this might be more unusual than we imagined, that the thing we are, curious, questioning, pointing instruments at the dark and asking who is there, might be extraordinarily rare. The next time you step outside at night and look at the stars, you are looking at 200 billion suns. Most of them are surrounded by planets, and on almost all of those planets, as best we can tell, tonight is a night like any other. The instruments keep returning empty. The pattern is absence. The sky remains unchanged. But here, on this particular world, in this particular moment of the galaxy's long history, something is. We are the only thing we know of that is asking. That is not nothing. And that is the most interesting thing we have found so far. Thank you for spending this time with me tonight. Good night.